So here's a lecture on section 3.2. It says a function will not have a derivative at a point f comma f of a where slopes of the secant lines fail to approach a limit as x approaches a. So what we're going to do is we're going to break down this statement, and then we're going to look at the practical applications of this and show that wherever we hit any of these four conditions, we will fail to have differentiability. So here's an idea. Let's talk about this idea about the slopes of the secant line failing to approach a limit. And let's do it with the example of this absolute value function. Let's say we want to explore the differentiability at this point, where these two lines come together to form a point. Now, let's call this point the A point, the fixed point. Let's say that we have this other point, which is found at position X, and X is a variable point. And what we're going to talk about is what is the slope of the secant line as X approaches A? Well, if this is the absolute value function, then we know that the slope between these 2 points right now, the slope is 1. But what happens if we move that point a little closer? Oh, the slope is still 1. And closer, the slope is still 1. So as X approaches A from the right-hand side, what we called yesterday, or in the previous lecture, the right-hand derivative, we would say that the right-hand derivative is 1. As the variable point approaches the fixed point, the slopes all the way down the line are 1. Now, let's change and say, okay, our fixed point is still here, but now we're talking about X being over here. And then we talk about the slope between those 2 points, the secant line slope. And here we see that the slope is -1. But what if we move that point closer? What happens as X approaches A? Well, the slope is still -1 and still -1, right? In other words, we might say that as X approaches A from the left-hand side, this left-hand derivative is -1. Remember, both the right-hand derivative and the left-hand derivative are limits. And these two limits, one from the right, the limit as X approaches A from the left-hand side, or this one, the limit as X approaches A from the positive side, these two limits, again, this is f of X minus f of A over X minus A, f of X minus f of A over X minus A, these two limits don't equal. And when we say that the right-hand limit and the left-hand limit don't equal, we say the limit doesn't exist. Well, if these two limits represent the derivative, we would say that the derivative doesn't exist. And we're going to call this situation a corner. Two different values for the right-hand derivative and the left-hand derivative, and they're both finite values. Now, it could be that when we do this, we don't get a finite value. Let's investigate what's going on at this point in the second drawing. Again, is the right-hand limit, as we do, just look at it through the lens of a right-hand limit and a left-hand limit. So let's say again, this is our fixed point A. This is a variable point X, and we've got a secant line. And maybe we could say that this slope is approximately 1. But what happens again as X approaches A? What happens to that secant line? I don't know what it is, but it's certainly bigger than 1. What happens if I leave those 2 points behind and get even closer? I don't know what it is, but it's certainly bigger than that second slope. And this next one, even bigger. I would say that as X approaches A from the right-hand side, I'd say that this limit, this right-hand derivative, is positive infinity. It gets steeper and steeper until I get essentially no slope, a positive, and it was, before we got to the no slope, it was all the slopes were positive. Again, let's switch colors. Again, focusing on this point here and saying, well, what happens as x approaches a from the left-hand side? Well, how about -1? How about I get closer? I don't know what it is, but it's certainly more steep and negative. It's certainly less than -1. It's getting more negative. And as I get closer, these lines, these secant lines are getting steeper and steeper. I might say that the left-hand derivative is negative infinity. Well, positive infinity, negative infinity, certainly different values. We would say whenever we have a situation where either the right-hand derivative or the left-hand derivative has either a positive or negative value, we're going to call that, instead of a corner, we're going to call it a cusp. Right? Hey, and those two values aren't equal, so we might summarize is that there's no derivative there. Just like we did over here. No derivative over here, because the right-hand derivative and the left-hand derivative, those two limits failed to equal each other, so the overall limit didn't exist. Okay, but what about a vertical tangent? Okay. Again, I'm only interested in investigating this one spot. Again, let's call this location on the horizontal axis A. Let's talk about X. Let's talk about X approaching A. So here's a point. Here's a slope. Here's another slope. Here's another slope. X getting closer to A all the time. You can see it going to, sorry, that's not a left-hand derivative. It is a right-hand derivative, and it's clearly looking like it's going to be infinity. If I go at it from the other direction, again, here's where X is. Here's a secant line that's going from that point on the curve to that point on the curve. And as X gets closer, we can see that these are getting more steep. But this time, the left-hand derivative also equal to 0. And well, you might say, well, that's great. They're both, sorry, also approaching infinity. You may say, that's great. They're both infinity. But does infinity equal infinity? Does that limit exist? Well, even the idea of limit would say that if the limit is infinity, it's really unlimited. So even though these have the same symbol, we still would say that the limit doesn't exist. Because the limit was equal to infinity. And if the limit doesn't exist, our conclusion then is no derivative. Okay? So there we have it. No derivative if we are approaching what's referred to as a vertical tangent. Last example we're going to do, and this is one having to do with a removable discontinuity. It ends up being true that all discontinuities lead to a lack of derivation. Okay, let's again go for the interesting point. Let's call A this point where our point is. Say X. Let's talk about what happens when X approaches A, at least from the right-hand side. So here's my point, and what do we see for that secant line point? To me, like it's 0. And this also 0, and this also 0. It looks like in this particular instance, the right-hand derivative is equal to 0. Now, it does not matter that the removable discontinuity creates a 0 or any other finite value. But we know that when we approach from one side, and that one side contains the point where the discontinuity is, then we're going to get a finite value. Let's just declare this to be a finite value. Whereas, what happens when x is over here and x is approaching a from the left-hand side? Well, look at that value. Okay, it's pretty steep. Okay, let's maybe call that 1. What happens as x gets closer? Well, it looks like it's getting bigger. And if x gets closer again, oh, the slope is getting even bigger. It looks to me like this slope keeps on getting more and more steep. I might say that the left-hand derivative is equal to infinity. And whenever we approach a jump discontinuity, that we are going to see that one side is going to end up being infinity. And infinity, about that idea, is never going to equal to the finite value that we see coming out to the other side. And again, our conclusion is, therefore, there's no derivative. I'm sorry, I think I earlier called this a removable discontinuity, as the notes say, but really what we have here is a jump discontinuity. What happens in a removable discontinuity? Now, let's just do a really quick drawing there. Okay, here's a removable discontinuity. Okay, and there's my A. So what happens as x approaches A in this case? Okay, getting closer, getting steeper, steeper, steeper. Oh, looks like this right-hand derivative is going to end up being positive infinity. What about if I come at it this way? So here's x getting closer to A, and you can see this one is going to end up being negative infinity. Okay, whenever we have a discontinuity, we have some either right-hand derivative or left-hand derivative that's going to end up equaling either positive or negative infinity. And if that's the case, when that derivative, that limit equals positive infinity or negative infinity, we simply say, it sure seems like the limit doesn't exist. And therefore the derivative doesn't exist. All right. Now, that's one way of attacking this problem, using the idea of looking at it graphically. Let's take a look at this second example where we're given the function in the form of a piecewise function. Okay, let's take a look, let's say, at the right-hand derivative. That derivative that's noted by limit as x approaches, and again, my most interesting point here is 0 of f of x minus f of a over x minus a. Oh, but we know the value of a is 0. What do we end up getting here? Oh, and this is from the positive side. So this is going to be the limit as x approaches 0 from the positive side. F of x, when x is slightly positive, that means I'm going to be using that definition for x. F of 0 is 4 times 0, which is 0. And this is over x minus 0. This looks like the limit as x approaches 0 from the positive side of 4x over x. The x's cancel. I get 4. Oh, well, that shouldn't be a surprise. When we look at that, that thing's a line, not a line, a line. That line slope is 4, and we found the derivative to be 4. Okay, that to me makes perfect sense. Okay, well, what about that left-hand derivative? The limit as x approaches 0 from the minus side of f of x minus f of 0 over x minus 0. Well, if x is a little bit negative, that means we're going to be using that definition. So this is the limit as x approaches 0 from the negative side of x cubed minus, and again, the value of this function at 0 is 0 over x minus 0, or the limit as x approaches 0 from the negative side of x cubed over x, which is the limit as x approaches 0 from the negative side of x squared, and that's a big fat 0. hey, the left-hand derivative is 4, the right-hand derivative is 4, the left-hand derivative is 0. Does the right-hand derivative equal the left-hand derivative? No. Our conclusion, no derivative at that location. There's a lack of a limit at that location. And how would we classify this particular thing? Well, the right-hand limit and the left-hand limit were finite, but they disagreed. I'll call that a corner. Okay, so we just looked at a bunch of exceptions. Some places where there was a lack of differentiability, but the good news is that these are exceptions to the rule. We really have to work hard to find functions that have a lack of differentiability. Most graphs that we deal with are smooth, that they are differentiable on their domain. And that's the good news. Okay. Second thing, something about differentiability that's going to help us out. And that is differentiability implies local linearity. That is to say that when we look at the curve close up, almost all curves will look like lines. So near a point of tangency, near a place where we're looking at a tangent line, the tangent lines and the curves themselves, at least over some little spans of time, will look nearly identical. Let's take a look at this idea of local linearity by looking at a very curvy graph. Okay, lots of curves here, and you say, well, it doesn't look very linear. Let's say right here. Well, let's zoom in on that and let's see if we don't see linearity. Okay, doesn't look linear yet. What if I go and zoom in more? Oh, that looks pretty linear. What if I zoom in more? That looks almost linear. Zoom in more. Wow. The more I zoom, the more linear it gets. So if I zoom in closely enough, it'll look linear, which means, again, tangent lines, at least nearby the point of tangency, will also look a lot like the curves themselves. All right? So that's good news. It also means that we can use some other tricks. Now, it is true that limits can be difficult to deal with. Absolutely. Okay. And in general, calculators are pretty dumb devices. They do what they told. They can't handle, many calculators can't handle the nuances of finding limits. But because we know that differentiability implies local linearity, we might do something like say, all right, what if we try to use that idea to at least get an estimate to the value of a derivative, to the value of the tangent line slope at some location? So I want you to imagine, all right, that I've got some function, all right? Draw out that function, x squared plus 3 looks like this, right? And let's say I'm over here at 2, right? And I know that if I zoom in closely enough, that this point on that curve will appear locally linear. Okay, sorry, I had a little technical glitch there. We're going to continue on. So the point I'm trying to make is that if I know that there's local linearity, I might think of having a place where I'm focusing very much only on that little spot, and it looks linear. What if I go a little bit below, call that H, a little bit above, call that H, and then find the slope that goes through those two lines. The slope that goes through those 2 points ends up being a relatively good estimate of the derivative at the point that's a little bit, that's in the middle, right? Again, we're going to go up h, we're going to go down h, and then we're going to say the slope for this distance 2h. So we're going to use x equals 2 as our point. So f of 2 plus h, and we're going to use 0.001 as our h, minus f of 2 minus 0.001, all over, and if we subtract those 2 points, we end up getting 2h2 times 0.001. All right? We'll need a calculator to calculate that. So I'm going to show you a little trick on the calculator that I like a lot. And that is, I've got a function that I'm dealing with. And that function, again, was x squared plus 3. I'm going to go to the grapher, and I'm going to put in the function x squared plus 3. Okay, that's the graph. We know what the graph looks like. I didn't do it so I could look at the graph. I did it so that in my calculator sheet, I make references to that function called f1. So for example, f1 of 2 is 7. Of course, 2 squared plus 3. 4 plus 3 is 7. But I could also do things like, hey, I wonder what f1 of 2 minus 0.001 is. Oh, great. Well, what if I do control division so I get a fraction, and I can say f1 of 2 plus 0.001 minus f1 of 2 minus 0.001, and I'm going to divide this all by 2 times 0.001. Great. And our estimate is 4, or at least some number that rounds to 4. So we might say that this is an estimate of the value of f prime at 2, and our estimate is 4. Okay, great. We can do that with a h value of 0.001, or maybe we just take 2 different points, find the slope between those 2 different points, 6 minus 3, difference of my y values, divided by 2 minus 1, the difference of my x values, 3 over 1, 3. 3 is the slope. Great. That's going through 2 points that are on some curve, and 3 is the value of that slope. What did we just do? Well, if the function, let's call it f, that goes through those 2 points is called f, what we just found was that f prime of 3, no, not 3, f prime of something is approximately 3. But f prime of what? Well, remember, the idea of the symmetric difference is that you have some point that you're trying to find the derivative of, or estimate the derivative, and you go up an h, you go down an h, and that's the value that we're doing for its estimate. Well, what's the halfway point between 1 and 2? Oh, sounds to me like it's 1.5. So just given these 2 points, we can say a reasonable estimate of the derivative of that function at the midpoint between 1 and 2, 1.5, is 3. And there we go. Let's switch gears a little bit, and let's just recall some other things that are good to know. Differentiability implies continuity. Every place where something is differentiable, we know that function also has to be continuity. We saw how continuity made things not differentiable So we're basically saying, you know, that means wherever place there is a derivative, it must be differentiable. So differentiability implies continuity. If I tell you a function is differentiable, then you also know that that function is continuous. All right. One more. Intermediate value theorem for derivatives. Oh, maybe we should do a quick review of the intermediate value theorem in general. It says that if a function is continuous on some closed interval from A to B, then there exists a C on the open interval from A to B such that f of C is equal to any value between f of A and f of B. In other words, when I know that a function is continuous, it must go through all the intermediate values in the y direction. That's IVT in general. But what does this IVT for derivatives say? Well, it says that if we know that we have some interval from A to B on which the function's derivative, that means the derivative must take on any value between f prime of A and f prime of B. Oh, so if I'm told a function has a derivative at 2 of 5, and if I'm told that it has a derivative of 7 at position 4, then somewhere between x equals 2 and x equals 4, there has to be a place where the derivative is equal to 6, as long as that function is differentiable on that interval. Functions take on all the values between points for functions that are continuous for IVT, for functions that are differentiable for IVT for derivatives. Okay. All right. So that concludes our discussion of section 3.2.